If you're working in dentistry, you definitely know that truly understanding how your patient's jaw moves isn't just important, it's foundational.
Absolutely.
Getting that dynamic relationship right is absolutely crucial. Doesn't matter if you're planning complex restorations, dealing with TMJ issues, or even, fabricating more straightforward prosthetic work.
It really is.
And let's be honest, digital tools are rapidly changing how we approach this whole area.
So completely. Simulating those really intricate movements outside the mouth,
Mm-hmm.
whether you're using, say, a physical articulator or working in a digital space, that's the key.
Right.
It's how you create restorations that don't just fit, but actually function harmoniously with the patient's unique anatomy.
Okay.
It's really about optimizing the bite, predicting the outcome before you even pick up a handpiece or hit print on the 3D printer.
Exactly. So this deep dive is all about getting incredibly precise with one specific piece of that puzzle, measuring condylar guidance angles.
Mm-hmm.
We're unpacking the insights from a very recent observational cross-sectional study. It's titled Comparison of Condylar Guidance in Opening and Protrusion using Electronic Axiography and CBCT.
Ah, yes. Lastman and colleagues.
That's the one. Published just this year, 2025, in Applied Sciences by Lastman, Yutowska, Teshuk-Pisik, and Yar.
And our mission today really is to take that specific study,
Mm-hmm.
pull out its key findings, and then sort of translate them directly into what it means for you, in your practice when you're making those crucial clinical decisions and planning patient care.
Let's jump right in then. First off, why are we even talking about condylar guidance? It all seems to circle back to the temporomandibular joint, the TMJ.
Right. You've got it. The TMJ is basically the engine of the whole stomatognathing system. It allows for all the complex motions we need for, vital functions like chewing, speaking, swallowing.
Everything, basically.
Pretty much. So if something's off there, it affects everything downstream. That includes the teeth and, of course, any dental work you place.
And when you're planning treatment that involves changing the occlusal surface, things like crowns or dentures, you have to replicate that patient's jaw movement somehow.
Yes, exactly.
That's where articulators come in, right? They're designed to mimic the patient's movement so you can build or adjust prosthetics in a controlled environment.
Precisely. And whether you're using a traditional mechanical articulator, those brass ones we all know, or embracing the newer digital virtual versions, they need to be programmed, set up correctly.
Okay.
And for that, you need specific measurements that capture the patient's unique joint characteristics.
And a study focuses on two main angles, the posterior determinants. Is that the term?
That's it. Sagittal condylar inclination, or SCI, is one. That's the angle of the path the condyle travels.
Yeah.
Think forward, backward, up, down plane.
Okay, SCI. Got it.
The other one is the transverse condylar inclination. You might know it as the Bennett angle. That describes the path during side-to-side or lateral movement.
Right, the Bennett angle.
Hmm.
But this study, it really zeroes in on the SCI, the sagittal one.
It does.
And there's been this kind of long-standing question in the field. When you're trying to measure that SCI value to program your articulator, which jaw movement should you actually use? Should you measure the angle during a forward protrusive movement or during maximal mandibular opening, wide open?
And that's exactly the question Lastman and colleagues set out to answer. Does the type of movement you record actually make a difference in the SCI value you end up with? And, maybe more importantly, which method gives you data that's most useful, most reliable for clinical application, specifically for setting up that articulator?
Okay, so how did they go about investigating this? What was the study design like?
It was an observational cross-sectional study conducted at the Medical University of Gdańsk. So basically, they looked at a snapshot in time for a specific group of people.
And who were these people? Who participated?
They had 30 healthy volunteers. Now, it's worth noting, they were a very specific group, young adults, all aged between 20 and 24.
Young.
And the researchers were careful. They screened them to exclude anyone with a history of TMD, any previous ortho treatment, or any facial trauma.
That's actually a really important detail. It means the findings are based on a young, healthy, you could almost say relatively ideal population.
That's right.
Which is definitely something to keep in the back of your mind when you're thinking about applying these results to your average clinical patient who, might easily have some of those factors.
Absolutely. It does limit the generalizability a bit, which the authors themselves point out. But, for studying the basic mechanics in a healthy system, it's a solid starting point.
Understood. Okay. And how did they capture the actual movement data?
They used digital axiography.
Yeah.
Specifically, the Modjaw system. It's quite advanced. This system tracks the patient's mandibular movements in real time using optical sensors.
Real-time tracking?
Nice. Yeah. They recorded several movements, but for this particular analysis, they really focused on repetitive protrusive movements, starting from maximum intercuspation, or MIP.
Which is basically just when the upper and lower teeth are fully biting together in their most usual comfortable position.
Correct. That's MIP. And they also recorded full mouth opening movements, again, starting from MIP. So they got real dynamic path data for both types of movement.
Dynamic tracking data. Got it. Was there anything else?
Yes, they also used CBCT imaging, a CareStream 9300 unit, to get detailed anatomical information. They were looking particularly at the vertical height of the glenoid fossa, the socket part of the joint.
Okay, so dynamic movement data plus the anatomical scans. How did they actually crunch the numbers then? Calculate the angles?
So they used the Frankfurt horizontal plane, the FHP, as their reference plane for calculating the SCI angles from that axiography data.
FHP.
Okay. Now, it's interesting. The paper does point out in the discussion section that using a different reference plane, like the axis orbital plane, or AOP, could potentially give you different, sometimes higher SCI values, maybe even up to 10 degrees higher.
Wow, 10 degrees difference just based on the reference plane.
Potentially, yes. But for the methods they actually used in this study, FHP was the standard they applied.
Good distinction to remember. The reference plane definitely matters, but for this study, it was FHP. And then for comparing the opening versus protrusion and seeing if they were related.
They used standard statistical tools, paired tests, to see if the average angles between the two movements were significantly different. And Pearson's correlation, coefficient to assess the relationship, the link, between the angles measured in protrusion and those measured in opening.
All right, that sets the stage perfectly. Let's get to the results. What did they find? What were the average angles they measured?
Okay, so looking at the average sagittal condylar inclination, the SCI, across both the right and left joints. For that protrusive movement, the mean SCI was about 56.6 degrees.
Hold on, 56.6 degrees. That sounds significantly higher than the 30 degrees or so you often see cited as a kind of average or maybe a default setting on many older articulators.
It absolutely is. And the authors make a point of highlighting this. It's a really important finding because it suggests that using these advanced electronic axiography systems, which capture the full dynamic path of the condyle, can reveal much steeper angles than maybe traditional methods suggested, or certainly steeper than just relying on population averages.
Yeah.
It really underscores why individual measurement is potentially so important, especially now with these digital tools becoming more accessible.
Okay, so 56.6 for protrusion on average. What about during full mouth opening? Was it similar?
For full mouth opening, the average SCI was actually slightly steeper still. It came in around 59.9 degrees, again, averaged bilaterally across all the participants.
Okay, so opening was a little steeper on average, maybe 3 degrees or so. But the real story here, the big clinical takeaway, wasn't just about the average number itself, was it?
No, not at all. The crucial finding, the one that really matters for thinking about articulator calibration, was the variability.
Ah, the spread of the data.
Exactly. This is where the difference between protrusion and opening was really stark. The protrusive measurements were significantly more consistent. The standard deviation, which measures that spread, was lower around 6 to 7 degrees per side.
Okay.
So most individual protrusive angles fell within a relatively narrow range. They kind of clustered between 50 and 65 degrees for most people in the study.
So if you measured protrusion on these 30 healthy young people, their SCI numbers were relatively close to each other, more predictable.
Exactly right. Now compare that to the opening measurements. They showed much greater variability, much more spread out. The standard deviation was higher here, around 9 to 11 degrees per side.
Noticeably higher, yeah.
And the range of individual values they saw was huge. I mean, while many were in that sort of moderate range, maybe 50 to 70 degrees, they saw values going from the mid-40s all the way up to nearly 90 degrees in some individuals during opening.
90 degrees, seriously. So someone could have an SCI of, let's say, 55 degrees in protrusion, which is pretty average according to this study. But then their opening angle could be drastically different, maybe 60, maybe 70, or maybe even 85 or close to 90 degrees.
Precisely that. The data showed quite clearly that while the protrusion angles were relatively clustered together, the opening angles were widely scattered. There's just a much bigger spread, meaning that opening pathway seems to be much more unpredictable and variable from person to person compared to the protrusive pathway.
Wow, that difference in variability is huge. Okay, so they're different in consistency. But are they at least related in some way? Like if someone has a steeper angle in protrusion, do they also tend to have a steeper angle during opening, even if it's more variable?
They did find a relationship, yes. There was a moderate positive correlation between the angles measured during protrusion and those measured during opening. The statistics showed a Pearson correlation coefficient, the R value, of 0.57, and this was statistically significant.
Okay, moderate positive correlation. So if you're steep in one movement, you're likely to be steeper to some extent in the other.
Generally speaking, yes. It suggests there's probably some shared underlying anatomical factor or maybe neuromuscular control influencing both paths. However, and this is key, the correlation was only moderate.
And what does moderate correlation actually tell us in practical terms? How tightly are they really linked?
Well, it tells us they're definitely related, but they're absolutely not the same thing, not interchangeable. If you look at the coefficient of determination, which is r squared, it was about 0.33.
Okay, 0.33. What does that mean?
It means only about one-third, roughly 33% of the variability they observed in the opening angle can be explained just by knowing the protrusive angle.
Only a third.
Only about a third. The other two-thirds of that variability are due to factors specific to the opening movement itself, or perhaps that individual's unique joint structure and muscle dynamics during that specific wide-opening motion.
That's a really critical distinction. It means you definitely can't just measure one, say, protrusion and perfectly predict the other, the opening angle.
Not at all.
The condylar paths during protrusion and maximum opening, while they're correlated, they are distinct. And that opening path is significantly more variable across different people.
Exactly. And, well, that leads us directly into the clinical takeaway, doesn't it?
It does. All right, let's bring it right back to you, the clinician sitting chairside or maybe planning at your desk. This finding about variability, especially the finding that protrusive measurements are more consistent, more reproducible, what does that mean for how you should approach programming your articulator?
Well, I think this study provides some pretty strong evidence. It supports using measurements derived from protrusive movements as the preferred standard for calibrating your articulator, particularly for setting that sagittal condylar inclination, the SCI.
So when you're gathering the data, whether it's with face bows and records or digital scans and axiography to set those dials or input those numbers into your virtual articulator software.
The suggestion here is you should prioritize the SCI value you get from a protrusive recording. Because, as the study showed, that measurement is more likely to be consistent, it's more reproducible, and therefore it probably provides a more reliable basis for simulating the patient's functional jaw movements on the articulator, compared to using a value derived from maximal opening, which we now know is much more variable between individuals.
Okay, so how does using that more reliable protrusive data impact the actual treatment planning and ultimately the care the patient receives? What's the downstream effect?
Using more reliable, more reproducible condylar guidance data logically leads to more accurate articulator programming.
Makes sense.
And this directly helps you reproduce the patient's specific functional dental morphology more effectively when you're designing restorations.
Because the angle of that condylar path dictates how steep your posterior cusp angles can be without running into interferences during function, right?
It's exactly that. As the paper discusses, the condylar guidance angle is a major determinant of occlusal morphology, particularly the angles and heights of posterior cusps. A steeper guidance might allow for steeper cusps, which can be good for chewing efficiency, whereas a flatter guidance angle requires flatter cusps to avoid those harmful premature contacts and potential problems like wear or fracture.
Okay.
So by using accurate, reproducible protrusive data for your SCI, you can tailor the occlusal design of your restorations, crowns, bridges, onlays, whatever it is, much more precisely to that individual patient's actual functional requirements.
And the hope there, the goal, is that it makes your prosthetic work more predictable, maybe reducing chairside adjustment time and leading to better long-term function and harmony with the joint and muscles.
Absolutely. That's the rationale. You're designing the restoration based on a more accurate representation of how that patient's jaw actually moves during function and near function, not based on an average or a less reliable measurement.
And where did the digital tools fit in, like the axiography system they used in the study? How do they help with this refined approach?
Well, these digital axiography systems are really key enablers here. They provide a level of precision in TMJ diagnostics that was, frankly, quite difficult or time-consuming to achieve reliably with older, analog methods.
Right.
They give you objective, real-time tracking of the mandible's dynamics. You can see the paths.
So they give you that consistent, reproducible, protrusive data that the study highlights as being so valuable for this purpose.
Precisely. They streamline the process of obtaining that critical data. And importantly, they can integrate it seamlessly into digital workflows for designing and fabricating the restorations. It's this kind of objective, individualized data that allows you to move beyond just using population averages or potentially less reliable measurement methods towards truly customized treatment planning based on the patient's unique movement patterns.
So boiling it down, the clear takeaway for clinicians listening seems to be, while the opening and protrusive pathways are related, they are not interchangeable for setting your articulator's SCI. Primarily because that opening movement is just significantly more variable from person to person.
That's right.
So for the most reliable articulator calibration, the evidence here suggests you should measure protrusion directly.
That really is the core message from this study, specifically regarding clinical application in prosthodontics. It provides solid evidence for favoring protrusive records for this specific purpose, setting the SCI.
Now, like any good scientific study, the authors were careful to point out its limitations. What were the main ones they highlighted?
Yeah, they did. The primary limitations they noted were, first, the relatively small sample size, only 30 participants.
Okay.
Second, the very narrow age range, just 20 to 24 years old. And third, the fact that all participants were asymptomatic, healthy, and had no history of orthodontic treatment or facial trauma.
So the findings might not directly translate perfectly to, say, an older population or patients who actually have TMJ signs or symptoms, or maybe those who've had previous significant dental work or ortho.
Exactly. You have to be cautious about generalizing too broadly. It's really a snapshot of a specific, healthy, young demographic. The authors themselves actually called for future studies with larger, more diverse groups of people, including symptomatic patients, to see how these findings hold up and if the variability patterns are different in those clinical populations.
Those are valid points. They temper the generalizability, perhaps, but they don't necessarily invalidate the core findings within this specific group they studied.
Correct. It provides valuable insight into healthy young adults, definitely. And it gives a strong basis for further research in broader, more clinically relevant populations.
All right, let's start wrapping this deep dive up then. The study by Lastman and colleagues, it really reinforces the power of these digital tools in TMJ diagnostics and gives us some pretty clear direction on which movement seems to matter most for a critical step in prosthetic planning.
Yeah, it really highlights that while condylar guidance angles during protrusion and opening are related, that much greater consistency you see in protrusive measurements makes them the more reliable choice for accurately setting the articulator SCI.
And for you, the dental clinician listening, incorporating this understanding perhaps by leveraging tools like digital axiography, if available, seems key to refining your workflow and hopefully delivering more precise, functionally harmonious prosthetic work.
It really is about moving from estimation or maybe reliance on less predictable measurements towards more data-driven precision that's tailored specifically to the individual patient sitting in your chair.
Absolutely. Now, just as a final thought, consider this finding again. The individual condylar angles they measured were often significantly steeper than what's commonly used as an average setting. And that variability in opening movements was so much greater than in protrusion. So if capturing this kind of real-time dynamic individual data truly leads to more predictable outcomes, how might integrating these precise measurements change your standard diagnostic workflow? Not just thinking about your most complex full mouth rehabilitation cases, but maybe even for seemingly simpler things like single crowns or smaller restorations where you might currently rely on less patient-specific information.
That's a great question to ponder.
Something to think about as technology continues to evolve and potentially becomes more integrated into everyday practice.